Alright, this is the key for dealing with test number 6 on the AP Physics 2013. The test was on Newton's laws, primarily in chapter 4. According to Newton's third law, forces only occur in equal and oppositely directed pairs, with two forces of such a pair acting on different objects. That's correct. It's if object A applies a force of some type on object B, then object B applies a force of the same type upon object A that's equal in magnitude and opposite in direction. So it's talking about the forces between two interaction. Forces always occur in pairs. If this one be B applies a force on A of whatever force that could be normal force, friction force, electromagnetic force, whatever, then A will apply force back on B that's of the same type, equal in magnitude, and oppositely directed. So they're on different objects. So this is true. If a body is accelerated by many forces, the resulting acceleration will be in the direction of the largest force. False. It'll be in the direction of the net external force. As an example showing this is false, let's say that I had 3 1 Newton forces applied like this. And on the other side, I applied a larger force, 2 newtons. These 3 Newton forces would overpower that 2 Newton, and the acceleration would be in that direction. It's where the sum is, not what any individual force is. Question 3. Mass is a quantitative measure of the inertia of a body. That's true. It's the desire of an object to go in a straight line at constant speed. Number 4. Newton's second law may be written as the sum of the external forces equal ma only when velocity is constant. False. It's not when velocity is constant. It's when the mass is constant. Inertia is the force that allows a body at rest to remain at rest. It's not a force. Inertia is a property a body has. It is not a vector. It is not a force. So it is not a force. Forces have direction. They're vectors. They require two objects to interact. There's no such thing here. Inertia is a property inherent to the body itself. Number 6. A person is holding a book in their hands. The reaction force to the weight of the book is. Now let's go back and think about this. So the book has a weight. Who's applying that weight? The earth is pulling on the book with the weight. So therefore, the book should be pulling upwards with a weight force on the earth. So it is the gravitational attraction of the book upon the earth. There's nothing says about the hand. Okay, the normal force of the hand on the book, its reaction force is the normal force of the book on the hand. Problem number 7. A force of magnitude F produces an acceleration of magnitude upon an object of mass y. A force of magnitude 3F is exerted on a second object, and acceleration of magnitude 8x is measured. What is the mass of the second object? Alright, so let's say we have a force F, and it produces on an object y an acceleration of x. Then we have a force 3F, and it's exerted on a second object of some unknown mass, and it produces an acceleration of 8x. So if I take this one and divide by the first one, 3F over F is equal to the mass times 8x over y times x. I can cancel the f's, cancel the x. So solving for m, I get m is 3/8 times y. Alright, let's go to the next problem, number 8. Number 8 says Object is moving to the right at constant speed. Which of the following statements must be incorrect? There is just one force acting on the object and it's to the right. Okay, so if there was a single object and it was acting on the right, what would that tell me? Well, constant speed in a straight line told me that the acceleration has to be 0 in this problem. But if I had that, the sum of the forces in x being max, I would get F is equal to max because there's one force, x and y, and it would not be 0. So this cannot be correct. There would be definitely acceleration and it would be to the right. Now there could be two forces and they could cancel, but if there's only one, that'd be wrong. There are no forces acting on the object. That would certainly mean there was no acceleration. There are a larger number of forces acting on the object to the right than left. I can still get no acceleration because I could have a 1 Newton force here, a 1 Newton force there, and a 2 Newton here, and AX would still equal 0. Remember, it says which of the following statements must be incorrect. It didn't say sometimes could be incorrect. If there was no net external force, sum of the external forces is MA. If that was 0, A would be 0. So the only one that is definitely incorrect is A. Problem number 9. A net force is exerted on an object toward the west. The statement that best describes this situation is, again, comes from Newton's second law. This is equal to MA. So if this is west, A is to the west. Now, so we know that much. So if we had a block here, say XY, where X is east, this thing has acceleration that direction. Does not mean it's moving that direction. Object may be moving north but will be slowing down. Okay, so it's going this way with V, but its A is this way. That A is not in the correct direction. The object must be moving to the west. Well, it could be moving this way and slowing down. Sorry, that'd be V, not A. If it's slowing down, the A could be in the opposite direction. The object will be accelerating to the west. That's right. It's acceleration, not velocity, that the net external force determines. Problem number 10 asks you to draw a proper free body diagram. You have a stationary block on a frictionless table. So you got something like this, and you have a block. Isolate the body, and then inventory the forces with what F. There's weight, there's no applied, there's a normal from the surface of contact. Make sure that you put it at the point of application and you show the arrow such that it separates the block from the table. T for tension, there are no ropes in the problem. Friction, it says it's a frictionless table. So that's it. Need an axis. There's an axis. Are there any of these vectors that do not lie along the y or x axis where I need an angle? No. This is it. We're done. Next one. A block moving through the air, neglecting air friction. Okay. I'll draw a block. And the block has weight. Does it have applied? No. It's flying through the air. Is it normal? No, it's not touching a surface in contact. Tension? No, it's not connected to a rope. Friction? Says neglect air friction. That's it. Just need a axis and you're done. Some easy points there. Alright, next problem. A 6.25 kilogram block starts from rest on a frictionless inclined plane with a 27-degree angle of inclination is shown below. Draw a proper free body diagram for this. Okay. I got a block like that. I have weight. I've got a normal. I have no applied. I have no ropes, no tensions. And it says a frictionless, I have no friction. I need to have an axis. It is convenient to draw my axis perpendicular to the surface. Like this. This will be X. This will be Y, just like what they drew in the block. And I'll need to have an angle here because this force is not lying along either the X or Y's. That angle there is the same as this angle here. What you did by rotating the inclined plane was you tilted the y-axis, and the y-axis used to be here along the weight, and you tilted it over, and that's what created this angle theta. What's acceleration of the block? To do this, we just simply apply Newton's laws. So sum of the forces in X is mass times acceleration in X. Forces, I had weight, and I'm looking for this side of the weight along X, and that side is found by the opposite side, so that's the sine function. So it's max. Weight is mg, so mg sine theta is max. I can cancel the m's, so I get ax is g sine theta. So ax is 9.8 meters per second squared times the sine, and the angle in this problem was 27 degrees. So the acceleration is 4.45 meters per second squared. That completes that part. Part C, what is the magnitude of the force applied by the block upon the inclined plane? Well, the force applied by the block on the inclined plane is the same as the force applied by the inclined plane. That's the normal force. Sum of the forces in y is may, but there's no acceleration perpendicular to the plane. I have the normal minus the weight times the cosine of theta, and I find that by, again, reading my free body diagram and realizing I'm talking about this side, which is the adjacent side. So that's equal to 0. N is equal to mg cosine theta. Therefore, the normal is equal to, I take the mass of the object, which was 6.25 kilograms, and I multiply by 9.8 meters per second squared, and multiply by the cosine of 27 degrees, and I get that the normal is 54.6 newtons. How far will it travel down the inclined plane in 1.75 seconds? Ax is constant, so kinematic equations are valid. Alright, so we're looking here for an equation, and I've got time, so this one turns out to be relatively easy. X is x naught plus vx naught t plus 1/2 axt squared. It initially was at rest, started from x equals 0 location. X is 1/2 4.45 meters per second squared times 1.75 seconds squared. The distance, 6.81 meters. This connects what we did in Chapter 3 to what we're doing here in Chapter 4. Alright, that does it for the first half of the test.